We are ready to resume our seminar with the third session. So this session will deal about two different topics. So the first topic is the topic of scaling that Jesse, that was already raised in previous presentation. And the second topic is the topic of weighting, which is is not really directly related to test scores, but is the other thing that many people reproach to economists when they use data from large-scale assessments that do not weight when they should. So Jeffrey Wooldridge will talk a little bit about this. But the first presentation is on scaling by Timothy Bond, who is assistant professor at Purdue University. Tim, the floor is yours.
Okay, so thank you for having me here. So this paper is, or what I'm going to be presenting is about, is it this button that goes? Green button. Okay, there we go. So this paper, or this talk is going to be based on two separate papers that Kevin and I wrote, or Kevin Lang and I wrote. One of them was published in 2013 in the Review of Economics and Statistics. The other one was published more recently in the Journal of Human Resources, both of which are getting at the issue of scaling in tests and how to deal with these issues. So, is there a way to go? There we go. All right, so if we think about why is it that, coming from an economics perspective, why is it that most economists are interested in test scores to begin with, is that it's basically the only way we have to measure human capital early in the lifetime. We don't get to see kindergartners going out and earning a wage, so we don't really know what their skill set is like outside of these sort of tests that we're giving them inside of a controlled environment. So when we think about an issue that I'm going to be talking about a lot as an example mostly here that motivated some of our work on this topic, the reason that we're mostly interested in the black-white test gap is that among adults, there's a large gap between blacks and whites in wages, and a large portion of that is due to measured skill differences. So we're interested in the black-white test gap because we want to know when do these skill differences emerge, and therefore what can we target, or when should we target different policies that would try and alleviate these skill differences. So the problem with this is that the published test scores measure human capital on an ordinal scale, not an interval scale. So they may have some interval properties, but it's generally not the intervals that we're particularly interested in measuring as an economist. So from our perspective, it's generally we're going to be able to see the rank ordering of students, but it's going to be difficult for us to interpret magnitudes of differences across students. So if we're thinking about this as a purely ordinal measure, there's an infinite number of ways you could cardinalize these rank orderings. All of them is going to give you a different conclusion about differences in human capital across groups or the effect of policy interventions on human capital accumulation. So there's going to be, the goals of this talk are basically going to be threefold. We're going to start off by briefly outlining why scale choice could matter. We've talked about this in the earlier sessions already, so this might be a bit of a refresher. And then I'm just going to use the black-white test gap as an example to demonstrate how sensitive the different results we could find are to alternative cardinalizations of test scores. What I'm going to show you is that looking at the black-white test gap, we can find a range of results basically from the black-white test gap is large at kindergarten and is eliminated by third grade to the black-white test gap is non-existent at kindergarten and grows to be large by third grade, all by using different scales of the test score. And then we're going to go move on to talking about how we can use adult outcomes to construct an interval scale that economists might care about. And it turns out that on that scale that we find that the gap in the black-white test scores is shrinking throughout schooling, which is the opposite of what you would find if you just used the published scale, which suggests that these scale differences really do matter for policy interpretations. So let me just start off with an example. This example, there's really no meaning behind this example. The only reason I chose these numbers was so that we didn't have stochastic dominance, in which case scale choice really wouldn't matter too much. But suppose we have 20 students, 20 white students, 20 black students. We're interested in measuring the black-white test gap. Test has only 3 scores, 1, 2, and 3. We have a distribution of scores, a distribution across by race across these scores. So if we showed these data to some economists who were interested in measuring the black-white test gap, what would they typically do? Well, we've got a score called a 1, a score called a 2, a score called a 3. We would take the average black test score, the average white test score, or maybe we would transform this to standard deviations first and take the average standard deviation score. Regardless, it's going to be more or less the same thing. So if we just took these scores at face value, we'd find that black's an average score of 1.8, white score 2.0, so the test gap is 0.2. All right, so what's the problem with this? Well, it implicitly assumes that the test score is interval with respect to whatever outcome it is that policymakers are concerned about. So why is it not necessarily natural? Well, suppose these are what the test scores mean. Suppose that score 1 means you can recognize the Latin alphabet, score 2 means you can read and write English, and score 3 means you can read and write English and Latin. Now, almost everybody in the audience would probably think that score 1 to 2 transition is a lot more important than going from 2 to 3, which based on the distribution we saw before would suggest there's a very large gap between blacks and whites. If we were thinking about maximizing the probability of being elected pope in the 800s, probably moving from score 2 to score 3 is a lot more important, in which case we'd be thinking that there was actually a gap in favor of blacks. So it does depend on what the scale is. In reality, what's going to matter is the size of the black-white test gap is going to depend on how we value these different skills relative to each other, how we value English fluency versus Latin fluency. So in general, the ranking of means between two groups is only going to be well defined if we have stochastic dominance in the test scores. Now that's a condition that can be satisfied in practice. It's a strong condition, but you can see it in things like the effect of Head Start on kindergarten test scores, for instance. However, even if that is satisfied, the magnitude of the difference is always going to be sensitive to scale choice. So there's always going to be some uncertainty about the magnitude of effect depending on what scale we choose. Now, if we're interested in something more complex than just measuring a difference in means, so when we're going to be looking at changes in a test score gap across time, that's going to be even more sensitive to scale choice. Now, it's possible that this is only a theoretical concern. Maybe the types of gaps that we're interested in practice are only, we only get differences if we have really wild or implausible scales that we impose on the test. Now, I don't know necessarily what a wild or implausible scale is, but it's possible we could come to some sort of consensus. So what we're going to start off by doing is basically explore this in practice by looking at how sensitive the black-white test gap is to alternative scales. So we're going to use two data sets here. The first one is from the ECLSK. The ECLSK is an American longitudinal data set that followed a representative sample of children starting in kindergarten, going up through third grade in the sample that we're looking at. And the reason that this is interesting for us is that a couple of influential papers by Fryer and Levitt in the early 2000s used these data to find that the black-white test gap was very small in kindergarten and grew rapidly by third grade, which had quite an influence on the direction of the literature on exploring where these racial differences came from. We're also going to look at a second data set coming from the Children's National Longitudinal Survey of Youth, which is going to use the PIAAC, which is a similar test to what the ECLSK offers. And we also find similar results to that, so it's a similar baseline for looking at. There is something striking about this data set, though, that there's another test that's given to them when they're young, and there's actually a very large black-white test gap. So just two different data sets. They're going to have different advantages for us, particularly because the CLSY is going to come into play when we try to anchor the scores to adult outcomes. So how are we going to start off here? Well, let's just take a step back and say, I don't know what the scale should be. Let's bound what the scale could, let's bound what the possible black-white test gap could be by looking across all possible scales. So what we did here is we just searched across a 6-degree polynomial. This is probably more flexible than we needed to do, where we're going to transform T being the published test score, and capital T is going to be our transformation. So we're going to go out there and say, what's the largest possible growth in the black-white test gap from kindergarten through third grade? By searching for parameters beta naught to beta 6, what's the smallest possible the growth could be, and sort of have a boundary over what we could possibly say without imposing an assumption about what the scale should be. We also just did an exercise where we tried to maximize the correlation between the initial test and the end test, which is sort of like maximizing the reliability of the test, so maximize the predictive content across tests. In the ECLSK, we're going to use the initial kindergarten test and the final third grade test. In the CNLSY, we're going to use this early age 4 test and the third grade test, the PIAAC. So here's what we found. Column 1 is our baseline gap. So that's essentially, this is the ECLSK. This is essentially also what Fryer and Levitt found. So what do we see? We see that in kindergarten, this is in standard deviations. In kindergarten, the gap is about 0.4 standard deviations. Nothing really happens by spring of kindergarten. It begins to grow in first grade. And then by third grade, we see a large jump. So in sum, what it looks like is that there's a small to medium gap in kindergarten growing rapidly by third grade. This is essentially what Fryer and Levitt found and published in 2004 and 2006. On the other hand, if we started to explore what we could have found with alternative scales, where we just take a monotonic transformation of this test score, the minimum we could have found in the ECLSK was that this kindergarten gap was 0.46, and nothing really happens to third grade, and as being 0.51. So the smallest possible gap we could have, smallest possible growth of the gap we could have found in these data was essentially flat, no movement from kindergarten through third grade. On the other hand, our transformation that maximized the growth of the gap, that's column 3, we find that the gap is essentially trivial in third grade. It's 0.11 standard deviations, in kindergarten, and by third grade it grows to be 0.75. So that's double the growth of what Fryer and Levitt found. So the range of possible conclusions you could draw from these data, if you're agnostic about what the scale should be, is that the black-white test gap is something between medium in kindergarten and flat through third grade to small in kindergarten to large in third grade and anything in between. Our column 4, where we're trying to maximize the correlation between kindergarten and third grade, actually doesn't look that different from the baseline. So if you thought that this was one way of finding a scale to maximize the correlation across tests, it looks like we're okay in that realm. I'm not saying that that is a necessarily good way. It's sort of a first pass at trying to come up with a scale that might be reasonable. Now, what about we go to the CNLSY for the PIAAC test? Column 1's again the baseline, and we see a pattern that looks very similar to what we see in the ECLSK and what we see in the Fryer and Levitt papers, where the gap in kindergarten is 0.25, so fairly small, and it grows rapidly to third grade to become 0.61. Now what's interesting about this is we look at the minimum gap, so we're instead going to choose a scale that minimizes the growth of the gap between kindergarten and third grade. We see a gap of about the same as we see in the baseline, but by third grade it's eliminated. On the other hand, the maximizing gap, so the biggest gap we could possibly find, starts off at 0 in kindergarten and grows to be 0.63 in third grade. So now we have an even wider boundary where it's basically anything from schooling causes, using the word cause very lightly here, schooling causes black children to catch up to white children, to schooling exacerbates gaps or creates gaps that were never existing between black children and white children. It's really the entire possible bounds of things that could happen. Our correlation maximizing transformation is a little bit different here, and it's interesting. We're maximizing the correlation between your pre-kindergarten test and your third grade test. We actually see a flat gap. So we see something very different than what the baseline would have told us if we had just used standard deviations of the published scale. Now, a question is, are these transformations reasonable transformations? Well, I don't really know what a good definition of reasonable is. We could have a discussion and sort of throw out a few different ideas. What I'm just doing here is plotting in the solid bar would be the 45-degree axis. That's our baseline scale. It just maps 1-to-1 between baseline and transformed scale. Our thick dashed line is the minimizing scale. Our thin dashed line is the maximizing scale. And these are coming from the CNLSY. And so what this is telling us is essentially what we'd have to believe about the correct scale in order to believe the conclusions that we reached. In other words, with our thin dashed line, our thick dashed line, which is the minimizing scale, that's the scale that we'd have to impose if we wanted to say that the black-white test gap was 0 in kindergarten, was large in kindergarten and shrank to 0 by third grade. So what this is essentially saying is that if we believed that there was no real differences in the skills that we care about between a baseline score of about 45 and, say, 115, but there were huge and economically important differences between scores between about 115 and 175, there would be no gap initially, or sorry, a large gap initially and closure by third grade. If we believe that what's really important are these high-level skills, not these intermediate skills, we impose a scale saying such, the black-white test gap shrinks rapidly with third grade. On the other hand, what does our maximizing scale say? Our maximizing scale says if we don't care about anything on the low end, meaning scores between a 0 and 45, the flat region of that line, are basically no real differences in economic importance, but then there's rapid differences over the rest of the scale, we'd end up with something resembling the maximizing scale, meaning that we have a large gap initially, or sorry, a small gap initially, and rapidly growing over third grade. In other words, we go back to a slide, you can justify 2 or 3 depending on what your beliefs are about what's economically important on the scale. So the bounding exercise is more or less uninformative. We could say pretty much whatever we want. We could justify it with some scale that's just a monotonic transformation of the published scale. We can find basically anything that we want. Now, what that means is that any conclusion that we have is going to depend on our choice of scale. So what scale should we choose? Our proposal is to anchor the scale to an outcome that policymakers care about. So what do I mean by that? Now, first of all, I should give credit. We're not the first people to come with the idea of anchoring. This dates back to some of the Heckman literature on child development. But applying it to the black-white test gap is sort of our contribution here and think about how we can overcome some of these scaling issues. So let's think about a theoretical framework. So suppose that we have some future outcome S, which is what policymakers care about. So let's say policymakers care about human capital because they care about maximizing wages of adults or maximizing educational attainment of adults, something like that. That future outcome that policymakers are trying to improve schooling for is our S. And let's say that it's predicted by some latent trait theta, and then we've got, I think that's a nu, is just some sort of error term in terms of choosing that. So we're going to assume everything here is distributed normally. The reason is that makes the math very easy. There's no reason to think that in practice these variables are distributed normally. In that case, everything I'm going to show you is just a linear approximation of the equations that are important. But the math works out really well when things are all linear. So our goal here is going to be trying to measure the racial gap in this latent trait theta, which is anchored to S, in terms of basically we're measuring the gap in some sort of latent skill that causes future schooling or future wages. So with a test, we're never going to be able to observe theta properly. The best thing we could possibly observe is what I'm going to call little s, is essentially theta with classical measurement error. So we've got to throw measurement error into the equation. But we don't even observe that. We don't observe that because the test itself, the scale, was not designed to have an interval property with respect to theta. It was designed to have some other properties. So the way to interpret this is that what we're actually going to be observing, t, is some monotonic nonlinear transformation of the latent variable theta. So the challenge is going to be how can we go from our little t to get to something that closely approximates theta. So we can't observe the function that goes from little t, goes from theta to little t, but we might be able to estimate it using the adult outcomes themselves. So if you think back to the sort of system of equations that we have, t is a measure of theta, which causes s. We can estimate the expected value of s given the test score, or basically the empirical equivalent of that, and possibly come up with our theta version of the test. Now, it's not going to be that straightforward, because what is it if we were to replace our test score with the expected adult outcome conditioned on test score? Well, there's two components to this. The first is our SIG, basically the test's informational content of theta, and the second is the mean value of theta. What's happening here is we're just applying Bayes' rule. Test scores are noisy measures of any sort of underlying latent achievement, and so we know when we combine a noisy measure, what we're going to get is a measure that's weighted towards the mean and a weighted combination of the mean and the information, depending on how informative that signal is about your future educational attainment. So this weight here, rho, is essentially the test reliability. It's the signal-to-noise ratio of the test, with respect to the outcome that we're interested in, this sort of latent trait theta which predicts our future outcome. So what that's telling us is that if we were to do this, we're essentially going to create a shrunk estimate of future educational attainment. And by the way, this is the right thing for it to do. We want it to be shrinking because our test is a really noisy measure of future educational attainment. We wouldn't want to, our best estimate of your future education based on one single test score is not going to be very good. It should be shrunk down to the mean. Now, why is this going to be a problem for our context, though? So let's use some asymptotics here. So this is just replacing the mean of our scores. So what we have in the first term is going to be the portion, okay. The first term in this next equation is going to be the mean S. The second term is going to be the mean theta. Well, the mean theta is just going to cancel itself out. What we're left with is our mean difference in actual achievement attenuated downwards by the test reliability. Now, what's going on here? The measurement error is biasing our achievement gap towards 0, and the more measurement error there is, the larger the bias. So what's happening here is that when we constructed our estimate for each individual was based off of a single test score. And a single test score is not a very good measure of one person's latent trait, so it's going to be shrunk down to the mean latent trait. But what we're interested in here for this question is the average group difference. So if we observe one black student with a poor test score, we're not going to be particularly confident that that single black student is going to end up having a bad future educational attainment or a bad future wage or has some sort of low latent skill. But if we observe lots and lots of black children all having low test scores, we're going to be much more confident in saying that on average, black children have lower latent skills than white children in this grade. So essentially what the problem is that we're over-shrinking our estimate because our estimate from our empirical mean outcome conditional on test score is based on the fact that we're only observing one observation, when in practice we're observing lots of observations for trying to calculate our group mean. So how can we try and fix this? Well, if we could estimate the bias induced by this shrinkage directly, we could just undo it. So suppose we had on our left-hand side our new test score, and on the right-hand side theta. Well, we could just run that regression, and beta 1 would tell us exactly how much S is underestimating theta. Now, obviously, we can't do that because we had the thetas, we would just use thetas themselves to calculate this. So it's just a theoretical exercise. But we do observe your future outcome, and your future outcome is a noisy measure of theta itself. So we can just replace this regression and run a regression of S on the future test or on our shrunken test scores. So let me go ahead and talk about how we're going to apply this in practice. So we're going to use our CNLSY data. And the reason that the CNLSY data comes back into play is that the CNLSY is great for this because the CNLSY allows us to observe the outcomes of children. Basically, we see test scores for children all the way going back to when they're 4 years old, all the way through school. And then we get to see their adult outcomes when they're in their 20s and their 30s. So we're going to calibrate our scores based on the educational attainment that we see for these kids by the time they're age 25. The reason that we use educational attainment and not wages is that when we wrote this paper, the children were not really old enough to have really good wage data. And they also, unfortunately, decided to hit the labor market right during the Great Recession. So even if they had good wage data, they wouldn't have jobs anyway. So they all got schooling. So what we're going to do is calculate our sort of rescaled test score. It's just going to be the empirical conditional mean. So it's the mean schooling outcome conditional on test score. We're calculating that separate for each single test score in each grade. We're not forcing this to be monotonic. Because of measurement error, in fact, it's going to be slightly non-monotonic at places. And we're also only going to use whites for this because we're concerned that if we used both blacks and whites, and blacks are near the bottom of the distribution in test scores, and blacks' educational attainment is determined in part by discrimination, we're going to get a really messed up matching of our adult outcome or that latent trait. So the way to sort of think about the latent trait that we're estimating is essentially the latent trait's ability to predict schooling for somebody who was white and had that latent trait. So I think it's still informative from a policy perspective. All right. So we can calculate that easily. Now the problem is, how do we calculate the attenuation bias that's going to be induced by this sort of measurement error in the underlying test. So we're going to run the regression of our test score on future schooling. It's going to be biased downwards because schooling is a noisy measure of theta, going back to the very first anchoring equation. The way that we're going to try and correct for measurement error in schooling is we're going to actually use the lagged rescaled test score in a leave one out context as an instrument for schooling itself. The reason that this worked is essentially by assumption. So each of our test scores is using, we construct our test score and its ability to predict future outcomes. If your test score could predict future test scores which predicted future outcomes, it would be in the test score itself. So any innovation year to year is going to be more or less random. So the test score last year is a good future measure of the adult outcome next year, and we're going to have basically use the IV then to correct for measurement error. So based on this estimate then, what we're going to have is we're going to calculate the average difference between blacks and whites on our rescaled test score, and then we're going to divide it by the beta 1 that we estimate. That's going to end up with some really messy distributions for the standard errors, so I'm going to report in brackets the 95% confidence intervals, which we bootstrapped to get around that. So here's the results. So keep in mind that this is the CLSY test that I showed you way back at the beginning, where if we just used the published test scale or standard deviations thereof, we found the black-white test gap was small in kindergarten and grew rapidly by third grade. Now here's us taking this in 3 different tests all the way out through 7th grade. So if we just look at the raw difference, as in we don't perform this correction for measurement error, we don't divide by beta 1 hat, we see something that resembles the published scale as well. So the math test is fairly large in kindergarten. This would be 0.57 years of predicted future educational attainment and grows to 0.72 by 7th grade. Kindergarten's going from 0.21 to 0.56. Reading recognitions are the reading recognition. The reading comprehension is the third column, is going from 0.24 to 0.6. Now watch what happens when we use our correction for measurement error. All of those low test gaps from kindergarten and 2nd grade, they all blow up. What's that telling us? Kindergarten, 1st, and 2nd grade tests do a very bad job of predicting future outcomes. Once you adjust for how much measurement error is in those assessments with respect to the adult outcome, the test gap is large, if not larger than it is in 7th grade. So if you look at these patterns, nothing here in terms of a difference between kindergarten or 1st grade and 7th grade is statistically significant. But if anything, the pattern suggests a very large gap between blacks and whites at kindergarten entry. And if anything, it shrinks by 7th grade, which is the opposite of what you would have found with the published scales. So to sort of start to wrap up here, the anchored scales are going to give, that we found anyways, give us a very different result than the published test scales. A lot of these differences seem to be due to really large measurement error in the first couple of years of schooling and the way that we, at least with respect to measuring a future outcome, and so adjusting for that's really going to be important. This, to me, suggests that thinking about the scale really matters. If we had found the published scales and the anchored scales tell us more or less the same thing, I wouldn't necessarily be harping so much on thinking about alternative scales here. The shortcoming, if you call it a shortcoming, is that the results are going to depend on the anchor. So if instead of using future schooling, we had used future wages, we could have gotten something different. We tried using the predicted log wage conditional education as an alternative measure. We found more or less the same thing. But you would expect that different anchors should give you different results because different parts of the distribution of aptitude or achievement or skills will predict different outcomes in different ways. So you have to think about what society is trying to maximize in determining what the anchor possibly should be. So suppose that we were interested in trying to minimize criminality, that naturally would tell us to focus on lower portions of the distribution of scores, which our anchor is going to blow up because those are the ones that presumably predict criminality very well. On the other hand, if we were trying to maximize the prevalence of PhDs, that probably would give us another different result as well because it'd be focusing on the really high scores and making those look really important. So there's a natural link between the properties of the scale you impose, the social welfare function that's causing you to impose those, and what parts of the distribution are going to be important, leading to the differences in the test gaps that we estimate. Now, downside here is that this is obviously going to be very data intensive. So the CLSY may be one of the very few data sets that would have allowed us to do this exercise. So what could we do in situations where we don't observe the future outcomes? You know, superintendents generally don't want to wait 25 years to evaluate the impact of their policies today. So one possibility would be to use a test that's been, you know, basically used by the CNLSY or some other data set that's been used for a long time, take the anchor that we estimate from there and apply it to the new generation of students. It's not going to be perfect. It's going to be essentially estimating the skills measured in a way that would have predicted, for instance, your ability to get schooling or your ability on the wage market, labor market in the 1980s, 1990s, or 2000s. But it's still going to provide us with some instinct on trying to provide a better way to interpret these scales. If that is all out of the way, generally what I tell people what's really helpful is just plot the distribution. A lot of times you plot the distribution, you're going to see right away that it's going to take a really bizarre alternative transformation to reverse the direction of the gap or reverse the direction of the growth in the gap. Now, sometimes that's not going to be very informative at all. So the example that Andrew showed us earlier that wasn't informative at all in terms of what was going on, it really, in that case, really does depend on the scale that you adopt. You need to think harder about what the scale you should adopt. When we plot the distribution, we sort of learn about what types of students are affected by the policy. And that is in itself interesting. Was it the low ability students? Was it the high ability students? It gives us a more robust way of looking at things than just focusing on the mean. Another situation, if all else fails, are there any other outcomes that you might have? If we could sort of show 5 or 6 different things all move in the same direction, I might feel a lot more confident that the difference in means of the published scale is reflecting a difference of achievement that we're actually concerned about as policymakers. All right, thank you.
Thank you, Tim. This presentation will be discussed by Peter Vereen, who is a senior research scientist at ETS.
Thank you. Thanks for the invitation to comment on this work. And thank you, Timothy, for sharing your 2 papers. I thought they were very interesting. I'm a psychologist, so by background, coming from psychological measurement, ending up in educational measurement. So that's a little bit different than economy and statistics, but I do have quite a few comments, I think, also relating back to the earlier discussion on interval scales this morning by Andrew, and the comments by Matthias. Let's see. All right. Oh, sorry, yeah. So, discussion of scale properties date back a long time, almost a century. The book by Campbell in physics, and the work by Stevens, which is most famous in, mostly referred to in psychology. And for test scores, there's some work in the 70s by Brogdon. He's actually from Purdue. Interesting for Tim, maybe. But also some more recent work by Benjamin Domingue. And even though it's sometimes mentioned that it's agreed upon that test scores do not have interval scale properties, this is not always the case. And the argument in favor of test scores having interval properties comes from the theory of additive conjoint measurement from mathematical psychology, the book by Krantz, mostly with contributions by Duncan Luce, are relevant, and I'll get back to that in a little bit. But what I wanted to also mention in the introduction here is that large-scale assessments like PIAAC and PISA and Pearls and TIMSS and whatnot, or the longitudinal studies that you were using in your work, they have 2 main sources of error. One is sampling, and the other is measurement error, and they are separate things. So, and sampling error is very complicated, but measurement error is also very complicated, especially if you want to combine things that have measurement error, like group means, differences in group means, and changes in group means, in differences in group means over time. So, a little bit about the paper. And the last paper, they use a relatively straightforward outcome, educational attainment, and they use gaps between groups in early education, and they express them in terms of eventual educational attainment. And they can do this because they have longitudinal data. Whereas in psychology or in education, normally you don't have the eventual outcomes. What we like to see there is that a test has predictive validity. For example, an admission test, does it predict how well people do in college or eventually in their profession, and not the other way around? So that's a little bit different. And what I wanted to mention about PIAAC is that, well, it's an assessment for adults, and you already have the educational attainment, so it's already available for that data. So it might be interesting to see if you can apply your approach of anchoring with that, because you have the data already. I did have some, the confusion is with me, so in the first paper, the 2013 paper, you argue that test scores, well, have ordinal scale properties, or are treated, no, have ordinal scale properties so that monotonic transformations are allowed, which is an admissible or permissible statistical operation in the terminology of Stevens. So you apply a polynomial, sixth order, but then you look at means and standard deviations of test gaps. And I thought, well, if you're looking at means and standard deviations, you treat your data as interval, because otherwise they are not meaningful. But then you get into the sort of paradoxical situations that you cannot treat, you cannot apply a monotonic transformation with that, if you assume that your data are interval. So I was a little bit confused about the discussion of the table in that paper with respect to the Stevens classification of nominal, ordinal, interval, and ratio data. So some other points, a little bit referred to in the beginning. Large-scale assessments are intended to measure group means or other statistics of interest related to groups, but they have measurement error. It's much more complicated to estimate a difference in group means because you have two variables that have measurement error. It's even more complicated to estimate a change in the difference in group means because you essentially have 4 measurement errors. And it's even more complicated in the data examples that you study, where you have longitudinal data. You actually measure people, in fact, with as far as my knowledge goes, about ECLS-K, with the exact same instrument in a couple of grades, where you also should, for example, take into account that there's an autocorrelation between the measurements. And to my knowledge, I don't think that is being taken into account in the scaling of the ECLS-K, at least. So just wanted to mention that there's a nice book, edited book by Chester Harris from 1963 about problems in measuring change, with a chapter by Carl Bereiter on some issues there with measurement error and correlated measurement error. And also a chapter by Fred Lord. And I think some of the issues that are discussed in that book are still relevant today, more than 50 years later. Don't need to discuss the last bullet, I think, longitudinal. Yeah, I mentioned that already. So let's look at some item response theory. So I mentioned that it's sometimes argued that item response theory models can lead to a scale that has interval properties. This is mostly argued for the Roche model, where the sum score is a sufficient statistic for ability theta. That relates a little bit to principle of maximum entropy in physics. And Matthias also mentioned some other relationships between IRT models and models used in physics, like the Ising model. So it has been argued that ability theta in the Roche model has interval scale properties. However, if you increase the discrimination, so the slope of the item response curve to infinity, you lose the interval scale property. So on your left, I think, yeah, you have the Roche model with a certain slope, which is equal for all items. And in the middle, you have a more discriminating Roche model where the slope is steeper. And in the final panel, if you increase that slope to infinity, you get what is known as a Mocken model, or used in Mocken scale analysis, and which is a model with ordinal properties. So by increasing the measurement precision in this situation, you're losing your scale properties, which is an interesting paradox, I would think. This was mentioned by Han van der Maas a few years ago, but I could not find a write-up of it. I just remember a presentation by him. But I think this is a puzzling situation in psychometrics, and is complicated in terms of what scale, to answer the question, what scale are we measuring? Another thing I wanted to refer to, that a few years ago there were two debates by this, well, I think it was the same debate in two different conferences by Wim van der Linden and Derek Briggs. They debated on interval scales in educational measurement. Is it an attainable goal or a myth? And they took quite extreme positions on purpose. And van der Linden's position was, well, it's a waste of time to quest for interval scale, because there are many examples in all sorts of fields, and he had a whole list in physics and statistics and medicine and whatnot, where measurements are expressed on a scale with unequal units, but they are still useful. For example, temperature or decibel, or all sorts of units don't have unequal units, but they are still quite useful in getting in studying certain variables. And he was arguing, well, test scores have norm referenced or criterion referenced interpretations that we should not alter, and can really be useful in being both in leading to useful theoretical and practical implications. And then Derek Briggs' point of view was a little bit different. It's not surprising, since if you know his background, he was a student of Mark Wilson, who was a student of Benjamin Wright. And Benjamin Wright was one of the main advocates of the Roche model in the United States. So he argued that the foundation of magnitudes of differences based on test score are a matter of debate, and we should conduct research in specific cases to establish properties such as interval scales and equal units. So you have to do double cancellation and so on your measurement variables to check if interval scale properties can be used. So I thought I thought to bring this up here because I think it's quite interesting. Then some other final notes. So test score scales are not equal interval. Is this a problem? I would say, would also lean towards Andrew's and Matthias's side. And we should not forget how scales were created. So step one in creating a test is specify the purpose of the test. What do you want to measure, and what do you want to use it for? For example, the PISA scale is norm referenced, which means that back to 2000, in the first cycle, the latent ability scale was fixed to have a mean of 500 and a standard deviation of 100. In the OECD countries in 2000. But now, almost 20 years later, there's many more countries participating in PISA. There's different OECD countries, right? Because more countries joined the OECD since back then. So all these changes need to still be kept in mind in interpreting the scale, I think. Well, I think as we saw in all presentations today, that measurement errors matter a lot, but also so do the confidence intervals. And I think in one of your last tables, you noticed that if you compare that with the initial table that was reported, the confidence intervals are really large and basically wipe out any trend in terms of significance. So that's why where you really see an impact of taking into account measurement error. And a point that was also mentioned, but I wanted to write it down, that item level data and questionnaire data are available. So if you want to do something different than is being done in the official reports, you can actually do it. So item level test and questionnaire data, and even more data like process data, response times, interactions with number of clicks, I think are even in the public database for PISA 2015 at least. So, and I think that's it. Thank you.
Thank you, Peter. So now we take a short break from latent variable because the other strong feature of large-scale assessment is that they're based on a complex survey design, so they come with survey weights. And so when you undertake secondary analysis, there's the issue of how and when to use these weights. And Jeffrey Wooldridge, who is a professor at Michigan State University, will give us his views about this topic.
Thank you. Thanks, Marco, for the invitation. I now feel my job is a lot easier now that I've heard that people are really worried about, interval scales and measurement error and item response theory. I'm just going to talk about, a very basic issue that comes up with survey data. Before I do that, can I be difficult and ask you to put that in full screen mode? Is that possible? I don't know, Control L, I think. Well, I think just Control L. Uh-oh, see, I knew it. I couldn't let well enough alone. Yes, thank you, okay. Okay, so as I mentioned, I'm going to talk about, this was a topic that Marco had suggested to me, so I'm mainly going to focus on regression analysis, but I will make some comments along the way about general econometric methods. Let's see, okay, there we go. So I'm going to quickly review different reasons for using weights in regression analysis, and actually not just regression analysis, but all kinds of analyses. And then talk about the linear model. And of course, the reason we use weights to begin with is because we think there's some well-defined population that we're interested in. If you always define everything you're interested in terms of the sample at hand, then of course the issue of using weights would never come up. So the talk will be, cover some results about why we should be interested in linear models, even if it's not the so-called correct model, because we still can learn lots of interesting things about the population by doing that. And then that will lead to a discussion of using sampling weights. So the final, in the section, the topic 4 there, I want to make sure I give you a framework where hopefully you can think through, after I give you the pros and cons of weighting, a scenario where you probably do want to use the weights even though you have a randomized control trial. Okay, so of course, long ago when I was taught econometrics, the first reason for using weights was because of heteroskedasticity. So we don't do that much anymore, actually. One reason is that we don't have to anymore, because if you're a Stata user, you put comma robust at the end of your command, right, and that's it. So that's actually a sort of good reason for not doing it. I always try to tell my students, if you're going to say you're not using an estimation method, there are good reasons to use it and there are bad reasons, good reasons not to use it and bad reasons not to use it. So a good reason not to use it is we don't need it anymore. It still could help with efficiency though, even if the weights are incorrect. A good reason for not using it, and one that I'm going to focus on in the case of heteroscedasticity, is that this will generally be inconsistent for the so-called linear projection parameters. And so I'm going to cover the properties of linear projections and then point out that there's basically only one estimator that consistently estimates those parameters, and that is the Ols Estimator. So I notice the Ols Estimator has taken a bit of a beating in this conference, but things that I say about it carry over to other methods as well. Okay, and then so I don't want to get too bogged down on this, but we know that of course weighting is done for treatment effects estimation using propensity score weights. I'll mention how one combines this with regression, because it actually does have something to do with using survey weights as well. And then a related problem is actually missing data, where you might have attrition or you might have non-reporting, and then that's very similar in many ways to using propensity score methods for treatment effects. Okay, and then the main topic of this is for survey sampling. And so again, the reason for thinking about this is we know that the sample was obtained not to be representative of the population that we're really interested in. And so this leads to some sort of stratification. It could be some sort of variable probability sampling scheme. It could be, and I'm probably the one who knows maybe least about this in practice than anyone in the room, and that is, of course, you have complicated combinations of this, where you have stratification in one stage and maybe variable probability sampling later on. You might even throw some cluster sampling in there. Okay, but I'm going to focus on basically the argument for and against using the weights. Okay, and that will carry over to pretty much any kind of scenario that you have. Okay, so there's still a debate, so I guess I skipped over this. It's pretty routine to see the weights used when you're reporting summary statistics, right? That people just naturally say, well, I'm going to report these summary statistics. I want them to be representative of the population, therefore I use the sampling weights. And that's, sometimes you see it done both ways, but nobody really complains about seeing the weights used when computing summary statistics. There's still more of a debate whether you should use the weights when you do, say, regression analysis, and what about for a randomized controlled trial? Should you use the weights there as well? So the issues there are, it depends whether the sampling scheme depends on the so-called dependent variable or the response variable, or does it just depend on the explanatory variables? Now, of course, in an ideal world, you would know which case you're in. I don't have to read code books for a living, fortunately, but some people have shown them to me, and I haven't been able to figure out how the weights were how the sampling was actually done. So you're given these sampling weights, and there's kind of a trust me, feature to these weights, where you're just supposed to say, look, these weights, they will, represent the population once they use them. Okay, so there's the issue of, is the sampling done on the basis of the dependent variable or just the explanatory variables? And then the other issue is, how much are you willing to assume about specification of your model? So are you willing to assume that you're such a good modeler that you have all nonlinear functions captured, for example? So do you actually have the conditional mean correctly specified? And so in general, there can be a trade-off between consistency and efficiency, which is a trade-off we often face when we do econometrics, right? So I'll try to make sure when you leave here, if you don't know this already, that you have some idea about what the issue is. Okay, so I'm going to start off by reminding you that specifying the population is important. For a lot of reasons, when you do treatment effect estimation, you should make sure that the population that you're talking about actually is an interesting one, that the units could actually be subject to the treatment. More to the point here, though, is that once you know your population, then you know hopefully how the sample was obtained from that population. Okay, but before we get to any sampling scheme, I want to just talk about features of a linear model in a population. Okay, so we're interested in things like, an educational production function where we have specified the population of students, or again, we have to be careful about specifying a population for average treatment effects. Okay, so standard notation, y is the outcome variable, the x's are the explanatory variables or the covariates. Okay, so as we do so much, we are using random variables to represent population distributions. Okay, so if we assume, so let's take the ideal case where we have enough controls so that if this is a policy intervention, then we know that we're interested in a conditional mean. So maybe one of the elements of x1 of x is a special element, maybe it's the key policy variable, and we've convinced ourselves that controlling for x2 up to xk essentially makes the policy intervention as good as random. Therefore, what would we be interested in estimating? Well, ideally, we would be interested in estimating the conditional mean, because once we estimate the conditional mean, we can estimate a treatment effect either averaged across the entire population, or we could, estimate treatment effects over subpopulations. The problem, of course, is that this conditional mean function can be basically anything, right? So we, of course, always write down fairly simple models, but sometimes we probably should admit more that we're very likely to be wrong, okay? So, what can we say about the model being wrong? So this is where this notion of a linear projection comes, or the best linear predictor comes into play. So maybe you didn't think you were going to see the phrase linear projection in my talk, but there it is, because I think this is a key to understanding about why it is you should use the weights and what the argument is against using the weights. Okay, so the population, the thing about this linear projection is that it's definitional. Okay, so unlike writing down a model for the conditional mean where you have always imposed some assumptions, this is a definition, okay? And so the population, and we know what the formulas are for both the slope coefficients and the intercept. These, of course, are the population formulas of the least squares estimator that you get in a sample, okay? So there's, of course, a direct connection between the linear projection in the population and how we estimate those parameters. And I should remind you that this can be very flexible because, of course, we can choose x1, xk. These things can be all the usual things: interactions, squares, logs, any kind of functions you want. Okay, so the point is that that this is definitional, and so this is a quantity we can always hope to talk about estimating. Okay, whereas the conditional mean requires many more assumptions to argue that we're going to get a consistent estimate of that. Okay, so the linear projection is equivalent to writing down a model. So if you hadn't heard that phrase before, I gather many of you have, if not all of you, but just a reminder that there's an equivalent way of writing this down as a linear function, which is a bit more standard, right? As we can write y as this linear function and then tack on this error term at the end, but this error term is only has the property that it has a mean of 0 and it's uncorrelated with each of the x's. Now, in fact, I would argue that most empirical papers that use ordinary least squares start off by writing that assumption, right? However, I think what we, and then you debate whether, you have all the nonlinear functions in here and so on. Of course, what we're really trying to do is get at the conditional mean. But why might we settle for this? Okay, well, I guess argument 0, which is the one we might have to settle for it unless we really are convinced that we're really good modelers and we choose the x's in just the right way. Okay, so the first thing is the important property is that this is the thing that's consistently estimated by ordinary least squares. Okay, so we don't need any other assumptions, right? So I know nobody in this group would say the errors have to be normally distributed or the errors have to be independent of the x's or anything like that. The thing that OLS is really good at is estimating those parameters of the linear projection consistently, and we don't need any other assumptions. Okay, of course so you know we're going to talk about why would one be satisfied with this if it's not, quote, the correct model. And then, of course, we know how to do heteroscedasticity robust inference, and one of the nice things about those standard errors is that they work asymptotically for getting the standard errors for those linear projection coefficients. So it all works out quite neatly. Okay, so here are the reasons we could be interested in it. First, it has an important approximation property, is that if you think about comparing it, you know, we're trying to estimate the conditional mean, it turns out that you can show pretty easily that the parameters in the linear projection provide the best mean squared approximation to the thing that we would really like. Okay, so in other words, these parameters are defined so that we get the best approximation to the thing that we would really like to have. Okay, of course, if you happen to choose well, then the conditional mean and the linear projection are exactly the same. Now, this doesn't mean, of course, that we're getting a great approximation, but this does mean that the parameters give us the best linear approximation, the ones that we're going to consistently estimate. And then this one is something that empirical people probably notice a fair amount. Again, this isn't universally true, but it's possible that by ignoring, you know, by just putting in flexible functions of the x's and estimating the linear projection, it's possible that you actually get good estimates of the so-called average partial effects. Some people like to call these average marginal effects, like stata, for example. This is a quantity that has a lot of interest because, for one thing, in the discrete case, it is an average treatment effect, and this is essentially what we do is we take the partial effect with respect to xj, and then we compute a weighted average of all the partial effects, right, to get a single number, and this measures the effect of xj on the mean value of y on average. So when we assume that we have the mean correctly specified, this is often the one number that's reported in a table, like when you do a probit or a logit or a tobit or something like that, right? It's this average partial effect that's actually reported. Okay, so it turns out that if you define this generally to be gamma j, there are some interesting, although certainly restrictive, theoretical results that say you could have the mean function misspecified and yet those linear projection coefficients give you the average partial effects. Now, even if this isn't true exactly, you kind of notice this happens a lot when you take a fairly simple model and you start adding stuff in. Since I don't have a ton of time here, I'll just show you. Here's one interesting case, though, where the true model is quadratic. So you include interactions and squares among all the x's. And you can show that if x has a symmetric distribution, then by leaving all of those quadratic terms out, so we would, in introductory econometrics, we would teach this as a horrible misspecification, right? But if x has a symmetric distribution, you can pretty easily show that that misspecification nevertheless gets the answer right on average, okay? And then there are some other results on multivariate normality of x where you don't have to put any restrictions on mu. But the point is that this linear projection may actually get us pretty close to something that's interesting. You know, it doesn't necessarily have to, but there are cases where we can show it does. And then estimating the linear projection can actually improve efficiency in randomized controlled trials. That is, you have a random assignment into treatment and control, but you don't have, especially small standard errors, if you have good predictors of the outcome, you can show that you don't have to impose any additional assumptions. You can simply use the linear projection apparatus to shrink the standard errors, okay, at least in a theoretical sense. Okay, so this, by the way, just to remind you, that, this is, to me, there's often this discussion about should you use a linear probability model, should you not? I think I saw, at least implicitly, some of them used in some of the talks today. The argument isn't about whether that's the right model or not. The argument is in terms of this linear projection, that this gives you the best linear approximation, and there are assumptions under which it gives you the average partial effects, okay? That way you don't have to try to argue with an econometric theorist about whether it's the true model or not. You just say, hey, I'm estimating the best linear approximation, and then the econometric theorist will go think about that for a while, okay? Okay, so this is, so in other words, I'm just setting this up so that at one point I'm just going to assert that if you want to always make sure you estimate this linear projection, then you should use the sampling weights. Okay, so that's going to be the bottom line, and then I'm just going to fill in some of the details in the next few minutes. Okay, so now let's introduce this idea of a sampling scheme. So let Z be the combination of X and Y. One way to think of the sampling scheme is that it's a stratification, and so you split up the population into mutually exclusive and exhaustive groups. And then, often what's done is you have to know something about the population shares, and then these tell us what, essentially, these are the probability that if you did randomly draw a unit from the population, what would be the chance of falling into each one of these sets. Okay, so what happens from here, of course, is that, okay, so in the case of standard stratified sampling, the weights are this, or they're proportional to the ratio of the sample shares, the population share to the sample share. And of course, what this is doing is this is giving more weight to units that are underrepresented in the sample relative to the population. Okay, so this is what the estimator looks like. It's kind of unfortunate that we also call this weighted least squares, because this weighting, of course, has nothing to do with heteroscedasticity. And so the reason for doing this is to try to consistently estimate some parameters. And those some parameters are the linear projection parameters. Okay, so as long as we start with the linear projection and we use the sampling weights, then you can show this estimator is consistent, just assuming that we're focusing on the linear projection. Of course, as a special case, we could have the conditional mean correctly specified, but that's not required. Okay, so as I'm sure many of you know, you can kind of go back and see the formulas. Of course, if this is stratified sampling, then you should, when you do inference, account for the strata as well as the weights, and accounting for the strata actually usually shrinks your standard errors. Okay, so this is kind of the key thing here, is that consistency of the weighted estimator only requires that you're estimating the linear projection. Okay, so something similar happens with variable probability sampling. The setup is a little different because here you randomly draw a unit from the population and then you keep the unit with some probability. So what happens is now the weights are the inverse of the probability of keeping the unit, and if you're being careful, you indicate whether you're keeping the unit or not with a selection indicator. So this selects out which units that you originally drew from the population you're keeping, and then you apply the weights. Okay, so again, whether you are in the standard stratified case or the variable probability case, or you combine the two, you can show that consistency only ever requires this zero correlation assumption, which again is equivalent to defining the parameters in the linear projection. Okay, so now the question is, I'm going to just take this head on now. Should we use the sampling weights? Okay, so the stratification depends, so there's one case where you clearly have to do this, I think, and that is if the stratification depends on Y, or if it depends partly on Y, if it depends on things that you don't know, if you don't know whether it depends on Y or not, then you should probably assume that it does. And so even if you have the conditional mean correctly specified, if you know that the stratification was based partly on your outcome variable, then it's difficult to justify not using the weights because you're not estimating anything consistently. You're not estimating the linear projection consistently. Even if the mean were correctly specified, you're not estimating that consistently either, okay? So the real discussion seems to be when the stratification depends on the x's. And so this might be geography, it might be some right-hand side variable like income if you're looking at student outcome type regressions. And so let's assume that the stratification depends on x. And so these are things you're controlling for. And so the debate seems to center on these two issues. Okay, so the one part of the debate is that if the conditional mean is correctly specified, okay, then the unweighted estimator is also consistent. Okay, so now this is important though because this requires two assumptions for consistency. Okay, it requires that the stratification depends on your covariates, and that you have the conditional mean correctly specified, okay? So, and then if we add those two things ensure consistency. And then if you add the standard homoscedasticity assumption, and notice this is all in the population, right? This has nothing to do with the sample or anything. This is all a population discussion. If you add the homoscedasticity assumption for you, then you can show that the unweighted estimator is asymptotically more efficient than the weighted estimator will be. Okay, so now you have two consistent estimators. One of them is asymptotically more efficient, so of course you would prefer the asymptotically more efficient one. Okay, so this efficiency argument argues against weighting, although I do want to point out one thing. This hinges on there being homoscedasticity in the population. It's possible that using the weights could somehow proxy for the heteroscedasticity, and it could actually be more efficient. Okay, but this is under the kind of standard Gauss-Markov assumptions. Conditional mean is correctly specified. Conditional variance is constant. Okay, so better move it along here. Okay, so the unweighted estimator is inconsistent if we only assume the linear projection. Okay, so in other words, even though stratification is based on the x's, okay, you're not going to get a consistent estimator of the linear projection parameters. That requires the conditional mean to be correctly specified. So the weighted estimator has this kind of doubly robust property. Okay, it works when the conditional mean is correctly specified, and it still gives you consistency when the conditional mean is not correctly specified. Okay, and so consistency, if you want to make sure you're always estimating something about the population, and that something is the linear projection, then you should use the weights. Okay, so here are the practical issues, of course. You use the weights and you don't use them and you get different answers. Okay, so now you go and maybe you like the unweighted estimates better. Okay, we're not supposed to say things like that, but it is the way it goes. And that the weighted estimates are imprecise. Okay, so now, can we justify using ordinary least squares without the weights? Well, of course, this requires you to be able to rule out the case that the stratification is not based on Y. But to give you something to take away if you haven't seen this before, this suggests a Hausman test, but the problem with using the kind of usual Hausman test is that would take a stand on which estimator is relatively more efficient, and we certainly don't want to do that. What we really want to know is, are these two things estimating two different sets of parameters, and that's it, because we know how to do robust inference in both cases. So here's a simple thing you can do, other than kind of go through the hard derivation of the robust Hausman test, is you can say, so you could take the first order conditions for the weighted least squares estimator, those are satisfied identically by construction, right? This is just the setting the first order condition to 0. And then you can say, well, what happens if I take this first order condition and I take the weighted least squares estimate and I put in beta hat? Then you can ask, is this sufficiently close to 0 that you're not worried about the difference between the two estimates, okay? So what this is equivalent to is adding the weighted x's to an expanded regression and doing an F-test on all of those weighted x's. And the null hypothesis is that OLS is okay. That's the way we usually do these things, right? Is you kind of say, okay, I'm going to take that I want to do OLS without the weights, and then I see if I reject the null hypothesis. So this is a regression-based version of the Hausman test. That's what this would be called. Okay, so let me just mention, so the bottom line is, I think that if you can trust the weights, okay, you should use them. Now, I was at a conference with some survey statisticians about 3 weeks ago, and I made that comment, and they started laughing. They said, you're saying that as if you can trust the survey weights. And I said, oh, you can't. And then, of course, you learn some things that you probably wish you hadn't learned about how these weights are actually done. But what I really mean by that is, if you really know the sampling scheme, you should be able to produce the weights, right, that do the right thing. Now, there are these things Jesse mentioned, that there's this raking and so on that goes on, but you know, you should still be able to trust those weights too. What I'm distinguishing between is things like when you use weights for missing data problems. Okay, now it's much less clear that you can actually trust weights like that, because that's based on somebody's model, not a sampling scheme that you should pretty much know about. So I'm going to probably stop here, because the interesting thing about this example, and I knew I probably wouldn't quite get to it, is that if you have a randomized controlled trial, so what you could do, of course, is just use the difference in means, right? And this is the case where you can try to improve, and I think I mentioned a paper with my, with a current student of mine, is that if you want to try to improve efficiency using regression adjustment, and the way you do this is you run separate regressions for the control and the treatment group. You have to use the weights, because this only works when you consistently estimate the linear projection. If you don't use the weights, you're estimating some strange weighted combination of the linear projection, and therefore, even though you have a randomized controlled trial, you're not going to get consistent estimates of the average treatment effect. So the interesting thing about this is you need to use the weights for 2 reasons in this case, and one is that you have to consistently estimate the parameters in the 2 sets of linear projections. And for theoretical reasons, you want to do one for the control group and you want to do one for the treatment group. Those you have to use the weights for. And then the second place they have to show up is when you average the differences in the fitted values that you get from estimating the 2 linear regressions. You need to estimate the population mean of the x's. And so in order to get a consistent estimate of that, you have to use the weights there as well. So even with the randomized control trial, if you want to, and whether you do regression adjustment or not, you have to use the weights in order to ensure consistency of the estimation. Okay, since I'm a little bit over, I'll stop there. The slides can be made available, of course, so you can go read. There are a few more slides there. Thank you.
Thank you, Jeff. And now we're going to have some few remarks from Sabine Meinck, who is head of research, analysis, and sampling at the IEA. And I'm sure she trusts her weights.
Okay, good afternoon to everyone. So I'm very sure that you're all craving for coffee, and I'm sorry that I have to keep you here for more 10, 15 minutes or so. I have some good news for some of you, which might be also bad news for others here, which is I realized that my presentation is the only one having no single equation in it. So, okay. So I'm working for the IEA, and since more than a decade, I'm involved in one or the other way in sampling, weighting, and variance estimation in all of the contemporary large-scale assessments. We have lots to do all the time, and so it is certainly a good idea to get out of our tunnel and look left and right, and there is not so many sampling statisticians in the world that are busy in this field. So it is really a great opportunity to get the chance to look at papers that have been written a bit outside of the educational researchers' world. So when I started to think about how I will get about this discussion, I actually started to read the note for this meeting here. And when I read that, I kind of started to be a bit excited about it. And I want to make it a little bit more broad than just focusing on the paper. And let me start with this here. So in the concept note for this meeting here, there is a lot of mentioning about primary and secondary analysis, and there's was a point made, and this is from the concept note basically. So the primary analysis, this is what it says, is mainly about efficient estimation of main parameters, the cognitive skills, most of the time in this case, in the population of interest. And it says that secondary analysis is mainly focused on the parameters of statistical model that aims at uncovering the causal relationship between different variables. So I left out some parts of the sentences here, but this is basically the main message here. So I really stepped back and I was thinking, oh, do we actually have here a definition of what is primary and secondary analysis? Now, I very well do realize that we use these terms all the time when we go to the conferences, but I don't think there has ever been something like a definition of what is this actually. And if we want to make up the stage here and say, let's define it, then perhaps we should take a step back and really think about it, because I personally, I'm not fully agreeing with what is said here. So basically my understanding is really primary analysis. This is basically what goes into the international reports. Why is it that, I mean, yes, it's true that we, in the international reports, which are still breaks if you print them out, right? They just scratch the surface of the data that we actually collected, right? And why is it that we just put here like simple statistical indicators? This is simply because there's such a wealth of the data and there's very limited time to come up with these international reports. Anyone who has ever worked in this field will know that the timelines are just crazy, and there is really not much time to do all the scaling, and I'm always so impressed. My colleagues are just done with the scaling for Thales and starting strong. It's really very dense timelines. So I guess there's no reason at all to forbid to put more sophisticated analysis into these international reports if there only would be the time. And I was just reviewing 2 chapters of a report that will come up that actually will use regression analysis in the international report. So much for this. Also, and moreover to this, the primary analysis is for sure still more broad than just measuring some domains, be it cognitive domains. Yes, achievement is most of the time one of our major outcome variables, but still, there's a lot more to this, even in the international or in the primary analysis. So I really suggest look it up and go a bit deeper into it. There's much more to learn about it. Now, with the secondary analysis, I'm also associated editor of our large-scale assessment journal. I have to review and read a lot of papers that basically present secondary analysis. So it's not in the international reports. And what I can say is that actually always they still do aim for making population inferences. They are not just interested in what's going on in the sample. And to be honest, I really sat down and tried to wonder why somebody would actually not be interested in making this inference on the population. So what would be the situation where I'm really just interested in what's going on in the sample? I had a very hard time to come up with any idea, and perhaps somebody here in the audience can help me with that. Perhaps I'm just not seeing the full picture of this. So now making the turn a little bit more to the paper that I'm supposed to discuss here, I would say, hence, this difference alone between primary and secondary analysis, for sure, in my view, no argument in altering recommendations about using the weights. So, of course, I cannot go into all the details of the whole paper that was presented, so I will just pick up a couple of issues. So when we ask ourselves, are now different weighting schemes needed? Honestly, my very honest opinion at this moment in time is perhaps not. So I think using sampling weights for design unbiased estimation of simple statistical indicators, that is really totally out of the question. So nobody would ever discuss this, or I haven't seen any debate about that, or not for a very long time at least. Weighting in simple regression analysis, so we heard a lot of comments here, and we will go deeper into that later on. Jeff also mentioned, at least in the full presentation, waiting for propensity score modeling, and I think he made a very good point in saying you should use the weights once you come up with your propensity model, so that makes totally sense to me. But then we also have more advanced methods that are basically also regression models, like multi-level models or structural equation models. And here we are a bit stuck, really. For the multi-level modeling, there exists, at the moment, I think, 5 recommended approaches on how to use the sampling weights in a multi-level model. And just PISA alone had changed the recommendations on how to use weights in their multi-level models 3 times. You can just look up the technical reports over time. It has been changing 3 times. However, I still haven't seen any proof which method is the best one. In addition to that, depending on which software you use, you get very different estimators. So even the parameter estimators are very, very different, not even with overlapping confidence intervals. So I think there is really a lot to do, and I would really step back and not say this is the right method or that. So I think we really need more research in this area. I totally take this critique that has been made over the day, I think, about the documentation. On one hand, people are complaining a lot that this is, 1,000 pages of documentation. At the same time, there's the complaint that the data is not documented well enough. So here again, there is this discrepancy between time and how detailed do we want to be. So I can promise the scaling chapter for the upcoming TALIS, and it's going to be presented, I think, still in June, is going to have more than 200 tables just related to scaling. So you can read a lot and get very much into the depths of this, even though we don't even have cognitive measures here. So good. Now let's jump a bit and pick up the next topic. I think, Jeff, you talked a lot about treatment effect estimation. So let me just say that randomized treatments can really hardly ever observed in the large-scale assessments. I used LSA as an abbreviation. There are lots of abbreviations around, and for sure, they are not randomized controlled trials. So in addition to that, somebody may say, yeah, but we can still use it as a quasi-experimental design. However, we already had this discussion in the morning, so if you use external variables and you impose them as kind of treatments, for example, some specific reforms in an education subsystem, then we may have some bias arising from the fact that we haven't considered this in the scaling model. As we all know, however, by now, the items are available, so you can very well come up with a new scaling model and include these new variables. And there are examples in the literature who actually did that. So, but still for me, I was questioning myself, is this discussion actually very relevant, because large-scale assessments are not treatment studies or RCTs. Okay. What else do I have to say? That's a bit similar, estimating causal effects for large-scale assessments. I really cannot get into the depths of this one, but Jeff, I also read your paper. I really enjoyed it with your colleagues. I think the title is "What Are We Waiting For?" And you talk a lot about causal effects there, right? So I'm not saying that we cannot use large-scale assessment data at all for modeling causal effects, but the circumstances must be very, very specific. A colleague of mine actually will soon publish a paper, and he has an extremely nice example where I'm really convinced you can do causal modeling. Read it once it's out. However, I just want to point out that there is a large body of literature by now with a very critical view about causal, the possibilities of uncovering causal effects with large-scale assessment data. For example, in 2016, in a large-scale assessment journal, there was a full special issue just on that. So I recommend dig it out. There's a lot of very interesting papers in this. So, and here I think, others have mentioned this before. I think this is a very nice setting here. So I think we have to talk more with economists and put people together in a room and talk with each other. Who knows, perhaps we figure out better ways in actually doing these causal relationship modeling. Okay, weighting reduces precision of estimates. So that was something I really stumbled over. I think you mentioned it in your paper, and you showed a very famous paper from the 70s or so, where basically the people were doing weighted modeling versus unweighted modeling, and the standard errors were bigger when you used the weights. Now, Peter mentioned it. Just for those that are not so familiar with the sampling theory, right? The standard error is made of two components in our large-scale assessments. At least we assume that it's just those two. There are probably more error sources. But there's the sampling error and the measurement error. And the whole morning we were talking about the measurement error. So these two error parts flow into the standard error for the achievement variables. All the other variables in the data set, the standard error is simply the sampling error. It's the same thing. Even for the achievement variables, the big portion of the standard error is the sampling error. Measurement error is just so small, right? So this is really a very important thing. Now, what we all know is once you use the weights, yes, they can have an effect on the standard errors, basically on the sampling errors. The effect can go into both directions. However, what it is reflected here is the true sampling variance that is induced by using, for example, a stratified or now, what's that? In a stratified design, you don't have an equal distribution of the sample to the different strata, or at least this can happen, and this is done very often. So if you would not use the weights, then the estimated sampling errors would be biased. And here, again, we are not just estimating means and correlation parameters or regression parameters. We are also just estimating the standard errors. Right? So this estimation might be actually biased. Whenever we teach that in our sampling workshops, we use that example to make that a bit more clear. So just imagine we have a country where we have like a public school system and then also some private schools. And the public schools, they all follow kind of the same curriculum, so they are very similar. But then we have private schools that follow a different curriculum. And the country may very well want us to select a sample in a way so that they can compare the private and the public schools. So we will oversample basically the private schools. So perhaps we have same proportion of private and public schools in our sample. However, in the population, perhaps there's just 10% of private schools or so. So if we do not use the weights, what we do is we overestimate drastically the variety in the school system. And as you probably know from your statistics course, the variety in a population is also related to the sampling variance. So we will also overestimate the sampling variance unless we use the weights and bring everything back into proportion. So my point here is that neglecting the weights, I think, unless I'm really missing something here, will lead to a biased sampling error estimation. Or in other words, the weighted least squares may produce higher standard errors. Yes, that might be true than OLS, but it will produce unbiased estimates of standard error. And as I said, it can go both directions. Can be bigger, can be smaller. Good. Yeah, the next point, and everyone was laughing here in the room, trusting the sampling weights. So can we trust the sampling weights? You wrote down to ensure consistency, use the sampling weights if they can be trusted. And I truly believe you have a very good point here. So being involved in all this sampling and computing the weights, I can say that generally all the procedures to come up with the weights, deriving the sampling weights, are methodologically sound and they are very well established. And I can for sure say that computing the design weights, so we can really trust the design weight portion in the weights. So for those that are kind of familiar, the estimation weights are made up by, it's basically a product of many different weighting factors. Yeah, and one factor is the design weights. The design weight is always related to each of the sampling stages. Usually we select first scores, then classes, then perhaps students, or PIAAC is very different for all the different countries, but basically the design weight is the inverse of the selection probability. So we can for sure trust into that because we get very reliable sampling frames. So for example, lists of schools, so we can track perfectly the selection probability from those lists. So I can see we can trust those weights. Now, there is a critical issue, I would say, with another portion of these estimation weights, and this is the weight adjustments. So we do weight adjustments also for each sampling stage for non-response. So we will have schools that reject to participate. We have individuals that do not respond in our survey. So in order to make up for that, we compute so-called weight non-response adjustments. And here we work with a very strong assumption that is the non-informative response model. And this model basically says the non-respondents are not at all different to the respondents. Now, everyone can argue very well that this might be a very strong assumption. And there's even evidence that this might be not true. So I had personally the opportunity to use a data set. It's called the PISA Plus survey. It was done just in Germany, where PISA was mandatory. So the participation rate was close to 100%. And a year later, it was a follow-up of the same participants, but this one was voluntary. Participation rates dropped a lot, and because we had the data from the PISA survey, we could do a very good non-response bias analysis, and we could tell that the achievement, socioeconomic background, and so on and so forth was very different between those who still stayed in the survey and those who dropped out. So this is a problem, I think. So the question that arises from that is, why don't we do something about it? And here we have really a problem. Again, there's a problem with timing. So we get the data back, we compute all the weights and the weight adjustments, we compute the participation rates, and a couple of weeks later, the reports should be out. So once we notice there is low participation rates, then we would have to ask the countries to provide us with some information about the non-respondents. So that information most of the time is not available at all. And if so, it's not available in time most of the time. And even if you do a very good non-response bias analysis, then this is still no proof that there's nothing wrong with the data. And this is basically why these large-scale assessments have so strict and high thresholds for participation rates. Okay, so in summary, let me end with this. I think I simply can enforce the statement, and it was on the summary slide, we haven't seen it. Basically, I would say Jeff made the point in most of the situations, you have to use the weights. There are some where I really think we need more research. This is debatable. Also, perhaps not so much that we use the weights, but perhaps rather in specific modeling types, how we use the weights. And there is more research needed. So I would like to end here with my recommendation. If you are not sure, use the weights. Thank you.
Thank you, Sabine. So we can break for coffee.